Hey guys, and welcome back to the CodeLab tutorial series for the Spiderman controller. So we're up to part 2, let's get right to it. What we have on the screen is where we left off last part of the project, and we've got this happening. So if we press play, our ball's going to fall to the floor, and we've got our bob here underneath the tether as a child. And you can see the velocity is moving along. So this tutorial, what we're going to do is get the ball, instead of just falling with gravity, to also be constrained to the rope that is between the tether and the bob. So I have prepared a presentation for you. How we're going to do that? We're going to use Valet velocity, which sounds scary, and the Wikipedia page for it is atrocious. But when you look at it simply, in our case, it's pretty easy and it's pretty cool, and I'll show you what it does. So Valet velocity for fun and profit. So feedback loop. This is what we're going to do each time we constrain our bob to the rope. So the first thing we do is add forces. So gravity, and we'll talk about damping later, but basically when we move the bob, we're adding forces to it. So that's the first step. The second step, and this is the cool bit, is we're constraining the current velocity to the length of the arm. So we sort of take where it's moved after we've added forces to it, and then we shorten that so that it's no longer past the length of the arm. And then, based on the old position and where it is after our second step, we predict the new velocity. So it will no longer go past the point. It will be constrained to the new point. And then we're saying, hey, we never went past that point. That never happened. We've just constrained it. So then we can predict the new velocity based on this new point. And then we just return it. So that's all well and good in words, but I can show you in pictures too. So this is the bob. This is our bob. Here's the rope. And you can imagine the tether point is this point up here. So the first step, we add the forces. So now, with gravity and its previous velocity, the bob's moved from this point to the new orange point down here. And you should notice something about this, which is that from up here to down here is longer than the length of the arm. You can see the arm length is this, so it'd be around here somewhere. So we're quite far past that point, which is where the next step comes in. So we constrain the position to be the length of the arm from the previous step. And then, once we have this position, we can say, well, the velocity that we're traveling at is from where the bob was in the first place to this new position here, instead of down here. And that's what lets us do this curve. So let's get into the code. Righto. So we're going to add a new method to our pendulum script, and it's going to be called constrain velocity. Or is it? Yeah, get constrained velocity, I think could be better. So we'll go public vector3 get constrained velocity. And it will take in our current position as a vector3 current pos, our previous position as a vector3 previous position, and a time, which can be a float time. There we go. So we've got some things we have to set here initially before we can start going through that feedback loop. So we saw that we're going to need the distance to the tether to work out how to constrain it. So we'll go float distance to tether. We're going to need something to store the constrained position. So vector3 constrained position. And we're going to need something to store the predicted position. So we'll call that vector3 predicted position. Right, so now that we've got those three things, what we can do is so the first step, so that was adding forces, that's already happened here because we're applying gravity, right? So we've added the force. Then the second step was where the magic happens, and that's where we'll call this. So we've got our new position based on this gravity, and then we're constraining it. So that is done like this. Constrained position equals vector3 dot normalize current pos minus tether position multiplied by the arm length. So let's go over that line. When we use this notation between, so these are two vectors, vector 3's, it means that we're getting a new vector, and that new vector is pointing in the direction of current position from the tether position. So it is going, it's pointing this way from up here. So that's how it works. It's getting the green line basically. That's why we multiply it by the arm length. So it's normalized. So it's just a unit arrow, an arrow of length 1 multiplied by the arm length gives us the length of the arm in the right direction. So that's the constrained position. Now we can move on to our predicted position. So our predicted position is equal to the constrained position that we just found out minus our previous position. There we go. Divided by time. So why do we do divided by time? Excellent question. I'm glad you asked. So the reason we do that is because this is a bit of a misnomer here. It's still a velocity. And the reason I say that is because velocity is equal to distance over time. So this predicted position, which is basically our velocity after we've constrained it, is equal to a vector that is pointed at the constrained position from our previous position. So this black arrow divided by time. And that's just the basic physics formula that gives us the correct predicted position. And once we've got that, that's basically it. So we've got one last thing to do, and that is to make sure that this is only happening if the distance to our tether is greater than the length of the arm. Because otherwise all sorts of funky things will happen that we don't want. Now I'm using a new code editor, and I've got to remember, I think it's Shift Alt K L? No, I don't know. That's all right. We also need to actually calculate this before we use it. So let's just do that as well. So distance to tether is equal to vector 3 distance from the current position to the tether position. Vector 3 distance, current position, and our tether position. And there we go. So if our current position to our tether position is greater than the length of the arm, so we've gone past the length of the arm, we need to constrain it. So we do this step. So once we've done that, we can just return it. Return predicted position. And if we don't do that, then we still need to return something, otherwise the compiler complains. So we return just the 0 vector. There we go. So now we've got our method. What we need to do is actually use it in this bob case. So what I'm going to do is I'm going to put it, for now, I'll put it above gravity. All that means is the very first time that this move bob function runs, nothing will really happen for the constraints. But after that, we'll have applied all of these forces to the position, and then we return, and the next time we come back in, we're constraining it based on that straight away. So I just like to do it that way. Get constrained velocity. Now, how do I set this up? Oh, so we need to use that to modify our bob velocity. So we'll go bob.velocity is equal to get constrained velocity. So we put in our pos, that's our current position. We put in our previous position, which we'll also need to set, I think. Yeah, we haven't set that yet, so we'll need to set that. And our time in this case is just time, because we're already passing that into this function in the first place. So we need to set our previous position. So when should we set that? We should set that after we've modified everything, but just before we return it. So, whoops. Let's not set that. Instead, previous position is equal to pos. Have we not defined previous position? That's interesting. Let's think about that for a second. Yeah, we haven't defined it at all, so let's just put it up here. And it doesn't have to be public because we're only going to use it inside here. Previous position. There we go. Right. So let's save that and see what happens here. Let's let it compile. Our scene's already set up for it because we're already calling the pendulum function in our swing script. So if we press play, let's see what happens. Ooh. Okay. So we've got a very slowly moving bob, which is moving ridiculously slowly. I'm not sure why that is, actually. Let's go back to our script and see what's going on. So we call move bob. And then we call our... So what we're doing is we're setting the velocity to this constraint instead of adding to it. So we need a plus here. Save that and let it compile again. And let's move the camera back a little bit so I can see it better. Oh, there we go. So as you can see, our ball is moving along, our bob, sorry, but it's got this weird motion to it where it's actually sort of jumping up and down. Well, let me just... It's like a bouncy ball. So the reason that's happening is because we're constraining the velocity. We just did that. The problem is we're only constraining the velocity when when the distance of the bob to the tether is greater than the length of the arm. That's the only time we constrain it. So what we need to do is add in some code to constrain it when it's shorter than the length of the tether as well. And that will give it a smoother curve instead of this jumping around, which is kind of cool. I like it. So how do we do that? Well, we've got to check in our loop here the distance from the position to the tether. And if it's less than the length of the arm, then we normalize it to the length of the arm. All right, so let's add that in as well. And we'll do it after we've changed the position, because we'll check the position. So here we go, if vector3 dot distance again, and this time we're checking against pos and tether position, and if that length is, no, we already did, less than the arm length, what we do is we normalize the position to be the length of the arm, but where it is. So we don't try and change it much, we just sort of shorten the length of the rope at that point. Is vector3, so we do a normalize again, and we'll multiply it by the length of the arm, just like we did before. So normalize, and it's going to be pointing at our current position, and we are doing it from the tether position, multiplied by arm length. Right, so now our current position is just shortened to the proper length of the arm. And then should we also set the length of the arm? I don't think we need to do that. Let's just do this. Let's just return position. See what happens if we do that. Save that. And let's run it. Whoa. I think we do. Ooh, okay, it's running again. I think we do need to set the length of the arm here as well to be equal to vector3 distance, not distance to tether, distance pos tether position. So it sort of refreshes the length of the arm there, I think. There we go. Look at that. Now we've got this beautiful curving motion that I'm not showing you because I'm not in the scene. There we go. Okay, so can you see anything wrong with this? It looks pretty cool, but it's not very realistic yet, because what's happening is we are swinging, and we're swinging, and we're swinging, and we're never stopping, ever, because there's no drag on this at all. So in the real world, what happens is there's air resistance, and as this moves along, the air hits it and reduces the speed at which it's swinging. So what we need to do to simulate that is get a vector that is the opposite direction to its current velocity, so the current way it's moving, the opposite direction to that, and it multiply that vector by some very small number, so that each frame there's just a little bit of resistance that will eventually make it stop swinging altogether. Okay, so we can perform that in the Bob, I think. So actually, whoops, go back to Unity and we'll go into the Bob script. So we've got apply gravity here. Well, that's easy enough. We can just do a apply damping function. So public void apply damping. There we go. And we'll need some extra variables for this also. So we'll need a damping direction and a drag variable. So our damping direction has to be a vector, vector3 damping direction, and our damp value or drag has to be a float, so that we can set that in the editor. We'll make that public float drag. There we go. End. Right, now we can set those things in here. So we already know our velocity because it's up here and it's public, so we can just reference that whenever we want. So what we'll do is we'll go damping direction is equal to negative velocity, so the opposite direction to velocity. And then we modify damping direction by our drag, which will be a very small value. And then we add it to velocity. So plus equals damping direction. So now that we've got that, see how there's 0 references here? We go back into our pendulum script and we'll have to add it in here after apply gravity. So bob dot apply gravity. There we go. I've just applied gravity twice. That's probably not a good idea. Let's do apply dampening. I don't know if I spelled damping, probably not an E in there. Damping. Apply damping, there we go. I can spell. All right, let's see what happens now. What I think will happen is nothing will happen because we haven't actually modified the value, so it will still go on forever. But if we go to our bob, now we go to our bob, yeah. We've got our drag here, which is 0, but if we set it to say 0, 0, 1, let's see what 0, 0, 1 does. Okay, so now we're moving, and as you can see, it's not even getting all the way to the top now. It's just slowly, with all the air resistance, coming to a halt down here. And I think I need to move the camera again, because let's move it like that. There we go. That's better. Cool, all right. So we've got that as well. And the other thing I'd like to do is also put a limit on the speed so it doesn't go berserk. Because at the moment, this isn't this is only constrained by the rope, not any other physics known to mankind. So it could go, 390 kilometers per hour. Could be a peregrine falcon. But we can stop that by adding another function, and this one will be capping the max speed. And we can do it in the same place we've been modifying our bob variables. So we can apply gravity, apply dampening, and then after all of that, we can cap the max speed. So we'll make a new function called public void cap max speed. And this will be pretty simple. All we'll do is we'll get our velocity and we'll say it's equal to vector3 dot clamp magnitude, and we put in what it currently is, so our velocity, and what we want, which is let's call it maximum speed, which means we need to declare maximum speed up here. That's all right, we can do that. It'll be public as well, so we can modify it. Public float maximum speed. All right, there we go. Save that. Let's go back to our bob. And now we have maximum speed down here, which is 0. So let's just check and see if it works. No. It doesn't work because we haven't added it in our main loop. So if we go back to our pendulum, we now have to say bob cap max speed. Save it. Back to Unity. There we go. So it's capped to 0. So it'll never go above that. Let's say 50. Yep. So it will never go above 50. Let's see what happens if we go to 10. A little bit slower now. Yep. I think 50 is a good value. Oops. Why is it playing again? Let's set it to 50. Save our scene. All right, we're almost done. All we need to do, besides the player controller, that'll be in the next tutorial, is to give our bob the ability to switch which pivot it's actually attached to. Because eventually our player will be able to just click on whatever they want, any part of the environment, and we'll tether ourselves to that. So that means we need to have the ability to move the tether point to whatever place in the world we need. So to do that, we can just have another method, and it'll be in our pendulum one because it'll affect the bob and the tether and the arm as well. So it's pendulum related. And we can just give it a new position, and that position we'll use to determine the new tether point. So let's create a new public void switch tether, and we'll take in a vector3 new position. I keep doing that because I was using Visual Studio 2015 before, and tab just let you go past that point, but I can't in Visual Studio Code. Not sure why. So we've got our new position. So when we call this, we can say bob transform. The parent of that is now null because we don't want it to be attached to the previous tether point anymore. And then we can say that our tether, or rather our tether transform position, is now equal to the new position that we've just given it. And then we can say bob tr transform parent. So the parent of our bob is now again tether transform. Then we go tether position is equal to tether. Lots of tether going on here, isn't there? Tether transform inverse transform. Look at my caps there. Point new position. So that's just to transform the position from the world space to the local space. It'll blow up if we don't do that. And we need to update our arm length to accommodate this new tether point, which could be miles away from whatever our previous one was. So we go vector3 distance from the bob to the tether. So bob transform dot local position and our tether position. Oops, again. Right, so 0 references. We need to be able to call this somewhere. So what we can do, so we'll just see if it all compiles. Yep. We'll create just a test script. Let's call it switch tether. Switch tether. There we go. And in this one, let's have just a public transform new tether. And we also need a reference to our, swinging script. So swing, let's just call it swing. And then in our update, whoops, we can say, if there's an input, say the spacebar, if input dot get key key code space, then we go swing dot pendulum. Yep, pendulum. Let's say switch tether, and we pass in our new tether position. New tether. Oh, that's not a position, is it? Oh, transform. Oops. Position. There we go. Save that one. Cool. All right. Home run now, guys. Almost there. Let's just create a new game object. Create empty. And we'll call this one our new tether point. So new tether point. Let's put our switch tether script on there. Right. So our swing object is attached to our bob. And our new tether is our new tether point. Let's go to our scene and see where it actually is. Okay, so it's sort of down here a little bit. Let's put it sort of halfway between. Doesn't have to be very precise. Just put it sort of down and halfway between the two balls at the moment, just so you can see it take effect. So now what happens is if we play the scene and we press space, you can see the ball's adapted to its new tether position. So it's working well. Let's try it one more time and see if I can get a little bit of a more interesting result. What happens if I do it now? There you go. All right. So we've got that new functionality. We've got swinging, we've got it constrained, so we've got air resistance and maximum speed, and now we can switch tether points at will as well. The very last part is to add the rope to it so we can actually see it, and also have a controller that we can run around with and make use of this really cool gameplay mechanic. So thanks for watching, guys. Hope you enjoyed it, and I'll see you in the next one.